Javier, please start your presentation. And please be sure that all your microphones are mute and you're not showing your video. And now I'm also switch off my video, video and microphone. This will make the connection and quality of the connection better. Okay, so please, Javier, your turn.
Okay, thank you very much. Can you guys see the screen of my laptop? Can you see the keynote presentation?
Yes,
okay,
yes, I see. Yeah.
Well, thank you very much first of all, for the invitation. It's a pleasure to be back in Norwich, even if it's only virtually. As Shasha said, I have great memories from my multiple times there, and I hope there are many more occasions for me to visit you guys and the other way around. For the moment, unfortunately, today I have to give the seminar from Madrid, more specifically from my kitchen. But well, I hope that the next time that we see each other, it will be in Norwich in a nicer place. Well, as Sasa said in the introduction, well, my name, Javier Rodriguez-Rodriguez from Carlos III University of Madrid in Spain. Today's presentation is going to be about a work that we submitted recently, actually last Friday, to Journal of Fluid Mechanics. It's co-authored by my colleague, Laurent Champigny, who is a Marie Curie Fellow here at my university, by Shasa, that you all know very well, and by Benoit Chaid from the University of Brussels, the Free University of Brussels. And basically, what we have studied is the classic deep coating flow that was studied in the 1940s by Landau, Levich, and others, but with a variety, which is that we consider the problem when there are two liquids, two immiscible liquids, to be more precise. And here you will see on the right part of the slide, you will see like one of the pictures, the experiments that we are like starting to conduct these days, where we aim at measure, at characterize experimentally some of the things that I'm going to describe today. Well, why are we in the first place interested about deep coating? Well, deep coating is an extensively used technique in industry, in material processing in particular, and it's a technique that allows us to deposit a thin film of a liquid on a substrate, on a solid object, typically. Where can you do such a thing, or where would you like to do such a thing? Well, in multiple fields. The first thing that may come to your mind, perhaps, is painting of surfaces. So here in the example, or in the pictures that I prepare, or we prepare, you see these globes that are being painted with this blue paint. The way to paint them is basically by dipping them in paint. Doing so, you deposit this a thin film of paint that eventually solidifies and creates the coating that you want, that in this case gives color to the object. However, one of the most interesting features of deep coating is that it allows for a very fine control of the thickness of the film that you deposit. Moreover, these thicknesses could be really small, as I will discuss later. So typically, you can deposit things in the range between a few microns to hundreds of microns, so and in a very well-controlled way. So you are able to deposit thin films and with a thickness that you know very well how to manage, how to control. Where do these things find application? Well, in plenty of branches of modern fabrication industries. For instance, in electronics, because you can create very thin films that endow the electronic circuit, the PCB, for instance, with anti-corrosion properties, or that allow our electronic circuitry to work in hostile environment with humidity and so on. So you can protect your circuit with a very thin film in this way. In optics, and actually from what I read, one of the most extended applications of deep coating is to fabricate, to manufacture optical fibers, like the one that we have here on the right. In optical fibers, typically the problem that you have is that losses. You also want to tune the fiber to work at a prescribed wavelength, or at a range of wavelengths. And the way to do that is to deposit some coating on the fiber in such a way that the surface, tell me that I'm sharing. Do you guys see me okay?
Yeah. Still okay, but now it's.
Do you guys see me okay?
No, No.
Okay,
No.
you see
Now
now?
it's too big. Yeah, perfect.
Perfect. Good.
Yeah, that is perfect. Yeah.
Okay, so I think you stopped hearing when I was talking about the applications of optical fiber. So maybe Google has something against me talking about that. So well, yeah. So these optical fibers, as I was explaining, they need some surface coating to guarantee the properties that you want, like reducing losses, tune the fiber to work at prescribed wavelength or range of wavelengths. And the way to do that is to deposit a surface coating the fiber such that light can reflect in prescribed ways on the surface of the fiber. Of course, fibers are long and you want to deposit the film kind of efficiently. So what you do is to pull the fiber, the length of the fiber, through the bud. So in that way, you guarantee that you have this very well-controlled film that you need on optical fibers. This is perhaps the most used application of deep coating in electronics and optics. But of course, anytime that you want high precision or high quality optics, like laser goggles or lenses and so on, you also want to cover your lenses with different layers that will allow, for instance, the glass to have anti-reflection properties, to filter specific wavelengths and so on. So also to do these things, deep coating is one of the available techniques. Also in material science, beyond optics or electronics, you may be interested in making your surface like hydrophobic, hydrophilic, and many times you can do that by, again, using deep coating to generate a thin film that, for instance, like in the example that we show here, endows the coating or the cover of this cell phone with hydrophobic capability. So water drops don't stick on it. For sure, I should not finish without mentioning biology, because it's one of the fields where deep coating is also very much used. Typically in biology, a problem that you have is that you want to functionalize surfaces. To functionalize a surface means to endow the surface with certain properties like biocompatibility, for instance. And to do that without significantly of the substrate, the geometry of the object, what you do is to dip this object into a bath that contains a solution of the polymer that you want to eventually coat your object, and then you gently pull, and magically you get that your object now is amenable to be used with cells. For instance, typically you coat things with collagen or some other protein that cells usually encounter in its natural medium. So elements that could be toxic, you can layer, micrometric layer, that cells identify as a natural component. So they are happy crawling on it or even attaching to it and so on. To such extent, this is a technique that is used in biology, that there are plenty of commercially available deep coating units, like the one that I'm showing here, where you can basically do deep coating in your lab just by pressing a few buttons, right? So as you see, the problem is very, well, the topic is very interesting. The applications are many, and here I'm just summarizing perhaps the most important ones, but you can find many more, right? And everything resides in the fact that you are able to control very well the thickness of the film using the theory of deep coating. Now, as I said, in many cases, namely optics, electronics, you not only want to deposit one film. Typically, you like to deposit several films. For instance, in optics, precision lenses can have up to a dozen or a few tens of different layers. Now, how can you coat an object with different layers? Well, in series. So basically, you dip your object in one coating, wait for it to dry, then repeat the process on another liquid, and so on. So the question that we were asking ourselves is, would it be possible to create a double coating in just one single dip? Right. So this is the main motivation of today's work. Like, can we do this deep coating thing with more than one liquid at a time? So to do that, or to answer this question, we are going to develop a theory of deep coating with two immiscible liquids. Before I go to the theory of deep coating with two liquids, of course, I need to review the key necessary concepts or the key elements from the original Landau Levich theory. For those of you who are not familiar with the Landau Levich theory, with the classical deep coating problem, I hope you guys will find this interesting. And for those of you who are already familiar with, what I'm going to do, I'm trying to focus on the elements that are important to be extrapolated to the two liquid configuration. So I'm not going to give here a comprehensive view of the Landau Levich theory. I'm just going to go through the essential elements. Now, in the Landau Levich theory, basically what we do is to divide the flow in different regions. So imagine that we have, like in the sketch on the right-hand side of my slide, imagine that we have this plate, that is the one vertical plate, infinite vertical plate, that is the one we want to coat with a thin film. Now, this plate is partially immersed in a liquid bath. Okay. At the bottom of the sketch, you see a region that will be the static meniscus. The static meniscus is this region that is determined by a balance between capillary stresses and gravity forces, where the flat film, the horizontal flat film, that will be the free surface of the bath, connects with the plate. Okay. Now, if there is no motion, if the plate is at rest, then what happens? Well, you just have your static meniscus. That is a hydrostatic problem that we even teach to our students. It's a simple thing. Now, what happens when you start pulling up the plate at a small velocity, at a gentle velocity? Well, what happens is that you are exerting viscous stresses on the liquid, and these viscous stresses are going to compete with the capillary forces, the capillary stresses that are keeping the static meniscus static, and they are going to distort it, creating a region where there will be a balance between viscous stresses and capillary stresses. That is the so-called dynamic meniscus, which is this intermediate region that I'm marking here, that I'm highlighting here. Of course, after a while, when you move sufficiently far upstream from the liquid bath, what you get is that the thickness of the film becomes asymptotically uniform, and this is the region that we will call flat film. Here, we are going to denote by H infinity the thickness of this flat film, and as you will see, is going to be one of the key elements on which we will focus both on the one liquid and the two liquid case. Well, how is the mathematical description of this flow? Well, basically, here you have the equation originally derived by Landau and Levich. This equation, to skip a few steps and to make the presentation last for less than 3 hours, I have already made the equation dimensionless using the capillary length of the flow, which is defined here as the characteristic scale. So basically, once you make the equation dimensionless, what it reads, when you can find, is that the flow rate, dimensionless flow rate, that is transported by the plate along its motion, is equal to the sum of the three terms with the three contributions that drive the flow. On the one hand, the first term, it comes from viscous stresses. So this H, thickness of the flat film, is the dimensionless form of the viscous stresses that the plate is exerting on the liquid. Now, the second term, which is proportional to this dk dz here, this is the capillary stress, or these are the capillary stress. Kappa is the curvature of the flow, of the free surface, right? So it would be the curvature of this gray line, which is the free surface of the flow. And then the third force that comes into play is gravity, which properly made dimensionless, and once this common factor is just a constant. It's the constant gravity, which of course is negative because it always tries to pull the liquid downwards. Now, how is this balance of forces in the region that is the dynamic meniscus? Well, as you see, the term corresponding to the viscous stresses, H, is always positive. Of course, the thickness is always positive, which means that, as expected, the plate always tries to increase the flow rate that comes with it. Contrarily, although it's not very easy to see here the sign of this expression, the capillary stresses are negative. So capillary stresses, capillary suction, as we typically call it in the Landau Levich theory, it will try to make the liquid not flow with the plate. It will try to keep the liquid in the meniscus. The way to see it's not very easy to see what the curvature does here, but the way to see that, if you come to the sketch, imagine the following situation. So here we have a high curvature, right, on the meniscus. Because the curvature is convex towards the atmosphere, it means that the pressure that you will have inside the liquid film in this region, where the curvature is large, is going to be therefore smaller than the pressure of the ambient. On the other hand, if you keep moving up all the way to the flat film is flat, so therefore its pressure, the pressure in the liquid film, is equal to that of the ambient. So here we have at the bottom part of the dynamic meniscus negative pressures, and here at the top part we have positive pressures. Of course, the liquid is not happy moving from low to high pressure, so therefore we expect the contribution from capillary forces to be negative, to try to keep the liquid as close to the plate as possible and prevent its entrainment. Okay, and of course, gravity, as I said, it just like pulls the liquid down and tries to keep it all the time in the bath. In this equation that contains the three key ingredients, this equation is eventually a third-order differential equation. Keep in mind that the curvature is proportional to the second derivative of the film thickness. And this equation actually can be solved with boundary conditions, which impose that the film is thin, far away from the bath, and that as we approach the bath, then, well, we converge to the static meniscus that is given by hydrostatic, okay? Well, in this equation, something that is remarkable, something that you may notice, is that there is only one control dimensionless parameter. So the only parameter that we have to control the flow is the capillary number. This defined like this is basically a balance between viscous stresses and capillary stresses, capillary forces. And this will measure, basically would be the thickness of the film, or this control, rather than measures, these controls will be the thickness of the film. Now, the theory that we want to investigate, let me move to the next slide, yeah. So the theory that we want to investigate is the conditions we want to investigate our theory are those that are most common in practical applications, which are when the capillary number is small. As you will see, if you really want to control a very well, or to have a very well controlled film, you need the capillary number to be small. And therefore, this will allow us to do an asymptotic treatment of the Landau Levich problem. So we are going to take advantage of the fact that this parameter is small to obtain a simplified description of the flow in the region of the dynamic meniscus. Okay. Now, what is characteristic of this region of the dynamic meniscus? Well, as I said, the viscous stresses in this region, they must become of the order, they must become comparable to the capillary suction. Otherwise, there will be no flow. Now, this is this one condition that we need to keep in mind. The other condition that we need to impose on this region is that the curvature of the free surface in the dynamic meniscus has to be of the order of the curvature of the static meniscus. So this region is going to take place, is going to live very close to the apparent contact line, the region where the static meniscus would touch the plate, and the static meniscus has there a curvature that in dimensionless terms is equal to the square root of 2, and this curvature has to be the same one that we have in the dynamic meniscus, because eventually two menisci, the dynamic and the static one, have to match each other. Okay, so these are two conditions that we need to fulfill. So what we are going to do to investigate the structure of the flow in the region where these two conditions are in place, we are going to use Landau and Levich used standard techniques in asymptotic analysis, although at the time they were not very formally developed, but they, of course, they had the physical intuition and they did it right. So what they did was to propose stretching of the variables. In particular, we are going to stretch the thickness of the film and the vertical coordinate, the stringwise coordinate, with a priori unknown powers of the capillary number. Of course, here we have these two unknown powers, A and B, these two unknown exponents. Applying these two conditions, we obtain two equations for the two unknowns, and this allows us to basically determine the two exponents. So we get that the stretching of the variables that is applicable and that gives us the size of the dynamic meniscus is that the height, the thickness of the film scales as the capillary number raised to 2/3, whereas the vertical extension, the stringwise extension of the flow, goes as the capillary number raised to 1/3. Now, when you plug these rescale or stretched variables into the original equation, it simplifies to this. And actually, you can now properly impose the condition that the capillary number is very small. This eliminates the gravity term. This guy comes from here. So basically, you obtain the classic Landau Levich equation that tells you that the thickness far away from the plate, the thickness of from the bath, the thickness of the flat film, is equal to the thickness plus this dimensionless form of the capillary stresses. Okay, this equation can be solved using a variety of methods. It's very simple and actually something that you can give as an exercise to a student. For instance, you can do it with a single shooting. and then you obtain a solution. I forgot to mention about the boundary conditions, of course. This problem can be integrated, as I said, with a shooting using boundary conditions, which are that the film is flat, far away from the bath, which means that the thickness is the asymptotic one, and the derivatives are equal to 0. And interestingly, the conditions when you move down to the bath, when you go upstream to the bath, the conditions are that the curvature has to be equal to the curvature of the meniscus at the apparent contact line, which is square root of 2. Let me draw your attention to something here that is important, which is that if you notice, I replaced the curvature by the second derivative of the thickness. This, of course, here we are using the lubrication approximation. In the lubrication approximation, the curvature can be assimilated to this second derivative. And this you can easily check also that with the stretching of variables that we proposed, then when you stretch the Z and H with the capillary number raised to those powers, then the nonlinear contribution to the curvature is negligible. It's of the order of capillary number to 2/3 and higher order terms. So basically, this is the problem that you have to solve. These are the boundary conditions. And if you solve it, you are able to obtain not only the shape of the free surface, which of course you get along the way, but most importantly, you get the main observable that we care about in our flow, which is the uniform thickness, the asymptotic thickness far away from the bath, the thickness that the flat film eventually will have. This thickness in rescale variables is equal to basically 1, is 0.95 or 94 something. And when you go back to units, then the thickness is of the order basically is equal to the capillary length times the capillary raised to 2/3. Now, to give you a taste of what would be the typical thickness that this equation represents, well, most of the liquids, they have capillary lengths, which are of the order of millimeters, right? Capillary numbers, typically, we are going to be working with values of 10 to the minus 3, 10 to the minus 4, something like that. So if you plug some numbers here, then you will get that basically you get thicknesses that are of the order of 10 microns, a few hundreds of microns, a few microns in that range. Okay, so typically we are going to get very thin films and very well controlled because, as you see, it's a viscous flow, it's very repeatable and behaves very well with the equations. And basically you get here the thickness that you need as a function of a very simple formula, okay? So this is basically the theory of Landau and Levich. Of course, we try to describe here what are the rigorous mathematical steps to solve the theory, but sometimes you don't need to go that far. Sometimes just a good old-fashioned order of magnitude analysis will tell you the relevant variables of the flow. And this is what I'm going to introduce here. So briefly, I'll get the scalings. And the reason why I'm talking about this now is because we are going to do something similar at the end of our problem, of the two-liquid problem, to try to obtain the relevant scalings for our films. Basically, there are two ideas, two conditions that tell us the size, the scalings of the dynamic meniscus. As I said, viscous forces.
There are questions one question from Mark.
Oh, there are questions, okay, because I don't see the window, so yeah.
Yeah. Mark, would you?
Thanks, Sasha. Sorry to interrupt, Javier. Could you just go back?
No, it's a pleasure, so I can drink my coffee.
So, when you solve your problem, so one slide back, is that possible?
Yes, sure. Here, yeah.
It was just, I had a query about the H infinity is unknown here, right? At the beginning.
H infinity is 0.95, yeah.
No, but you don't know it before you solve the problem, is that right?
No, you don't. Oh, that's an interesting, yeah. So actually, there is one, yeah.
It seems to be known in your boundary condition.
Mm-hmm.
Is it effectively like an eigenvalue here then?
Indeed, it's precisely an eigenvalue. So this is one of the details that I skipped, but I'm glad that you asked because now I can explain that more in detail. It's precisely an eigenvalue of the problem. Yeah.
So really, my question is it unique? Are there other H infinities that work?
Good question. If there is no gravity, the eigenvalue is unique. If you introduce gravity in the problem, things get a little bit more complicated, and therefore, if you keep this term that we decided to neglect, this capillary number to 1/3 that I'm highlighting here, then when you introduce this number, then there is a variety of possible solutions for H infinity. Okay. Of course, in reality, even though the capillary number is never zero, otherwise it means that the plate is just not moving, right? Mm-hmm. So in reality, you can get different thicknesses. Okay. However, this is a very nice PRL paper published in 2008 by Jacques Nuijer. What happens is that, well, you can basically go from this regime where you only have this eigenvalue, the 0.95, to the regime where you can have a variety of eigenvalues. You can go from one regime to the other experimentally by pulling faster and then slowing down the pulling speed. So in that way, you can sort of make gravity effects come into play, and then you can obtain different thicknesses. Okay, but let's say that if you pull sufficiently fast, you always find experimentally this single eigenvalue, right? So mathematically, coming back to your question, which I guess it was also like, mathematically, can you obtain more eigenvalues? No, the eigenvalue is unique as you neglect this capillary to 1/3.
Okay. Okay, right. Thank you very much.
And actually, well, the way this problem is solved, and Landau and Levich do some beautiful change of variables in their paper. You apply one more change of variables, so you define a variable eta that would be h divided by h infinity. In that way, the equation becomes free of any parameter. Then you can shoot from the infinity, which can be done with the change of variables that Landau and Levich propose. And then what you do is to shoot backwards, to shoot to the static meniscus, and there you impose that the curvature is equal to the square root of 2. So to be able to catch the right value of the curvature, square root of 2, there is only one value of the parameter h infinity that allows you to do that. So this is how you actually find out the eigenvalue, right? So it's very elegant the way Landau and Levich do it. Yeah, here I tried to skip a few details, so that's why just like I swept under the carpet and said, yeah, this is the boundary condition, right? But it's a little bit more subtle, as you realize.
Thank you, Javier.
Thank you very much. Anyway, so yeah, so I was saying, yeah, these are I was coming back to this. So there were these two conditions that we needed to impose. One condition is that capillary forces are of the order of viscous forces, that the curvature in the dynamic meniscus has to be of the order of the curvature of the static one. And again, like introducing L as the length of this, the stringwise length of this meniscus, then, well, you write this, and then finding out H and L between the two equations, you recover these scalings, okay, which are the ones, of course, that you get with the rigorous theory. Well, so far, I didn't tell anything that was new. This was known since more than 80 years ago, plenty of time. Now let's go to the party. Let's go to the interesting part, which is what happens when you have two liquids in the bath. Well, first of all, to go deeper, let me describe the notation so we don't get lost during the explanation. We have two liquids. The liquid one that we will try to represent in blue whenever possible. The thickness is going to be H1. We have liquid 2, typically represented in orange, whose thickness is going to be H2. And therefore, we have two interfaces. Interface 1 that separates the two liquids and has a surface tension sigma 1, and interface 2 that separates the outer liquid from the atmosphere and has correspondingly the surface tension sigma 2. The properties of the liquids are denoted with the corresponding subindex. And one comment, of course, notice that the density of liquid 2 has to be smaller than the density of liquid 1, otherwise the static configuration would be unstable. And crucially, there is this parameter that we didn't have in the one liquid problem, which is delta H. Delta H is the thickness of the supernatant layer of liquid 2 in the static bath, far away from the plate. Okay?
Javier, sorry. Sorry, Mark, are you having another question?
No, sorry, is my hand still up?
Okay, sorry.
Sorry,
yeah.
All right, it's gone.
One question, so please continue.
Keep the hand like this, but in a physical talk, no one would do that, no?
yeah.
So, no, it's okay. So this is the parameter that we are going to use also as a control parameter in this flow. Of course, we are going to use the same assumptions that we used before. The liquids are Newtonian. We are going to use the lubrication approximation. So the films are going to be slender in the region that we care about. The two liquids have to be immiscible. Otherwise, there will be diffusion, mixing, and more complicated stuff. And again, we will focus on the regime where the capillary number is small, because that's typically the regime that we want to use in practical applications. Okay. Now, how much more complicated it is our flow now, because we have two liquids? Well, actually a lot more, as you can see here. So if you make the problem dimensionless, then you don't have one parameter, the capillary number. You still have the capillary number, of course. The guy didn't go, but now you have 4 more parameters. Well, capillary number, of course, defined on the properties of one of the liquids. We choose liquid 1, for instance. But then now we also have the dimensionless thickness of the supernatant layer. So this delta H has already been made dimensionless with the capillary length defined in this way. And of course, you have 3 property ratios: density, surface tension, and viscosity ratio. 5 parameters, okay? Well, this is way too much. I think nowadays no journal would take such a long paper. So then we need to decide which parameters to study. And of course, we try to focus on those that we can, well, that we believe are going to have a larger impact on the flow structure and the flow dynamics. So these 3 are going to be the 3 ones that we mark in red. Okay, so we are going to change in our study the thickness of the supernatant layer, surface tension ratio, and viscosity ratio. Why we are not going to consider why we are going to fix the density ratio to a prescribed value with 0.885 is because using most of the liquids that we may want to use in this kind of flows, this ratio is not going to really change much. So it's going to be 0.80 something, 0.9, but we don't really expect a lot of variation. Okay, so this parameter we will rule out from our study. It's a little bit more interesting to discuss why we are not going to change the capillary number, which we are going to keep equal to 10 to the minus 3 throughout this study. Actually, I said before that in the one liquid problem, the capillary number is one of the main problems, one of the main parameters, because it's the one that we have that allows us to control the thickness, right? So why don't we focus on its study here? Well, first of all, because as you will see, the problem, the two liquid problem, also can be rescaled with the same power of the capillary number as I introduced before, and therefore the capillary number is going to almost disappear from the mathematical problem. Of course, we will keep it when we will go back to dimensional variables, but it will not greatly affect the structure of the flow. This is one reason, but perhaps the most interesting reason is because, as I'm showing later, actually the capillary number, changing the capillary number has pretty much the same effect as changing the supernatant layer thickness. So it means that because practically you can get the same effect changing one or the other, we are not going to study the two parameters or the influence of the two parameters. We would rather restrict to only one that we are going to take to be, or we are going to make it to be the thickness of the supernatant layer, okay? Regarding the variations or the scales that we are going to, or the ranges that we are going to study of these parameters, you will see that the supernatant layer thickness, it will change by order 1, basically, so between these values here. The surface tension ratio, we're going to study 4 possible values that correspond to common fluids that we may want to use in the lab. Think of glycerin solutions as the lower liquid and water glycerin solutions as the lower liquid, different oils as the top liquid. So typically, you are going to get these values of the surface tension ratio. And the same thing goes for the viscosity ratio. And actually, the viscosity ratio, if you see this, is the one that we are going to allow, or we are going to be allowed to change the largest range. Because, of course, if you use, for instance, silicone oil as a working fluid, then the silicone oil, you can get like basically any viscosity from pretty much that of water to 1,000 times that of water without substantially changing the density or the surface tension. So the values that we have chosen for these parameters are already thinking of possible like experiments, possible configurations that we can build in our lab, okay? Now, with these ideas in mind, now let me go to explain a little bit how is going to be the mathematical structure of the problem. Good news, as I said before, many of the things that we learned from the one liquid problem still apply to the second or to the two liquid one. And in particular, the equations that we obtain, they kind of look similar, although a little bit more complicated. So basically, we get two equations for the two thicknesses of the interfaces, right? And these equations, they have a similar structure, as I will describe before. So in these equations, well, you get like these are third order differential equations. You see, you have here the higher order derivatives, and the boundary conditions that you need to apply are identical to the one of the one liquid case as you move far away from the bath, as you approach the flat films. So basically, you require that the flat films are flat, right? It is more interesting, and this is what I want to explain a little bit better, what happens when you when the films approach the bath, when the films approach the static menisci. When they approach the static menisci, the basic idea that their curvatures have to be those of the corresponding static menisci still holds. So we are going to impose that the curvature, second derivative, of film 1 is equal to that of the meniscus 1 close to the contact line that is represented here by this blue dot, and the similar condition applying for the for liquid 2, for the interface 2. Okay, so on the one hand, we also need the curvatures to be the same. But however, differently to what happened in the case of one liquid, here we need one more condition. In particular, we need to specify that not only the curvatures of the interfaces take the prescribed value, also these interfaces, they have to keep a distance between them that is consistent with the thickness delta H that basically measures the distance that the two menisci will have far away from the dynamic meniscus. So it means that we can not only impose the curvature, we need to impose something else. So if you keep the the smallest contribution that allow you to incorporate this effect, the rate of separation of the two interfaces, you discover that what you have to do is, beyond imposing the curvature, you need to impose that the two thicknesses approach the static menisci as these two parabolas. Of course, the terms in the square root in these parabolas, they are the corresponding curvatures, but notice that these parabolas, they also incorporate the effect of where the two contacts appear on the plane. In particular, if you do some change of variables that I'm not going to describe here, you can see that the parameter that at the end of the day influences the structure of the flow is not any of the heights of the two menisci separately, but rather the difference in the height between the two virtual contact lines, delta C. And this delta C, if you work it out, you can calculate its expression using simple hydrostatics. Then you get that this delta C, as you see, is a function of the supernatant thickness, or the thickness of the supernatant layer, some fluid properties, and the capillary number. So here you have the explanation of what I said before. Changing delta H and the capillary number may have the same effect if you change them appropriately on the structure of the flow as if you only change one of them. So that's why we don't track, we don't take into account the changes of the two parameters, because as you see, touching this or modifying this can have the same effect that would have touching this one, okay? So basically, as you see, the problem is a little bit more complicated to solve because, well, you need to integrate these equations. The shooting technique that I was explaining before for the one liquid case cannot be applied here. It's just too stiff, the problem, and you need to do something else. And eventually, as we described in the manuscript, if you're interested in taking a look at that later, we use a time marching method. So here, this is the steady version of the equations, but that we developed the transient one in the manuscript, which is mostly used for the numerical method. Well, so like this is basically the problem that we need to integrate. Just one quick comment, because also time is going fast as usual. One quick comment, the structure of the problem, as I said before, is very much the same as the original one liquid Landau Levich. So if you take a look at these f functions that we have here, at the end of the day, they're polynomials of the thicknesses. So basically you have that the thickness of the flat film is equal to the thickness at any given position, plus these two terms that account for capillary effects that are third derivatives times third order polynomial. More complicated, but functionally speaking, not different from the one liquid Landau Levich equation. You can see that the functional form is identical. Now, well, as I said, we can solve this problem using, for instance, time marching, and then we end up with solutions like this. Give me a second. It's water, don't worry. So, so here is a numerical solution, the steady dynamic menisci for a given set of parameters. No? Here, well, the first thing that you see, we plot basically the same solution, but blowing it up at 3 different levels with 3 different levels of magnification. So here, basically, you see on panel A, the top left panel, you see the 2 static menisci, hydrostatic menisci, and that are like indicated with dotted lines, blue and orange. And then you see that there is a region up here, we denote B, to be the corresponding dynamic meniscus. Of course, we expect the dynamics meniscus to be a lot smaller than the static one because of what I said, because the capillary number is small. So therefore, to resolve this region, we blow it up, and we do so in panel B. So panel B is a zooming of the dynamic meniscus. So here, the dashed lines or dotted lines, they are the approximations, the static menisci. And you see that actually they touch the plate because this is the way you compute them. But then you see that the dynamic menisci, which are the solid lines, you see that they indeed don't touch the plate, but instead they start to bend until eventually they reach a uniform thickness. Something that is quite remarkable, and I will comment about that later on, is that is how disparate, how different the thicknesses of the 2 films are. In fact, if you take a look at panel B, you basically see that after the dynamic meniscus, there is like only 1 film. So you don't really tell that there are actually 2 films here. However, if you blow up the region denoted by C, and we do so on the bottom left panel, there you see that indeed, if you zoom in appropriately, you are able to tell that clearly there are 2 separate films. However, notice that the thickness of the outer film, the blue and the orange solid lines, is very thin. It's like several orders of magnitude thinner than the inner film, the one of liquid one. Okay, and in fact, this is going to be one of the most salient features of the flow that we will explain later. As I'm the same, basically you will see that I put a lot of attention on the thicknesses, and in fact, this is the main observable of our theory, both from the theoretical and practical point of view. At the end of the day, you care very much about what is the asymptotic thickness, because this is the thickness of the film that is going to code your object. So the rest of the discussion is basically going to be devoted to understand the result from the simulations regarding these 2 observables. And we are going to define, as we have done already, the thickness of the inner layer like this, like H1 infinity. And we are also going to define the thickness of the outer layer like delta H infinity. Okay, so these are the 2 variables that we will care about. So now, running our simulations for a range of parameters, as I described before, we can obtain maps of the different thicknesses, the inner and the outer one. So let me explain briefly the kind of plots that we obtain before we can start to discuss more in depth the physics. So here, the left column, these are maps of H1 infinity. That's the thickness of the inner film. On the right column, you have maps of delta H infinity, thickness of the outer film. On the top row, we have a given surface tension ratio, which is smaller than 1, right? Typical of glycerin water solutions with oil or something like this. And there you have another surface tension that is larger than 1, typical, for instance, of water and olive oil. No? Then in these maps, the color represents like the corresponding thickness, H1 and delta H, and vertical axis, we represent the thickness of the supernatant layer, whereas on the horizontal axis, we represent the viscosity ratio. Now, main features of the flow. The first one that is noticeable, as we said before, is that the typical thicknesses that we are going to get for delta H are a lot smaller than the thicknesses that we are going to get for H1. In fact, whereas H1 keeps values of the order unity, as given by the Landau Levich theory, surprisingly enough, the thickness of the outer film is a lot smaller. As I said, typically 10 to the minus 2, 10 to the minus 3 times that of the inner film. Okay, so that's perhaps the most interesting conclusion. correspondingly or consistently with that, then we see that sometimes the thickness of the outer film is so thin, and these are the black regions in these plots, it gets so thin that its practical existence should be put into question. Basically, they wouldn't exist because such a thin films here, if you plug numbers, we can be talking about thicknesses of the order of nanometers, tens of nanometers, things that are very thin. So basically, the very existence or the very stability of these films should be put in question. So they wouldn't exist, right? Of course, in these regions where there are no two films, because one of them is just too thin to be stable, it doesn't make any sense to talk about what the inner film would do, because all the results that we are obtaining today start from the assumption that we have two films. So basically, we have what we call existence islands, and these are these regions denoted by this dashed red line on the contours that mark the region where we actually have two films with thicknesses that could be observable or at least could be stable. Another interesting feature that we can observe is that the values of delta H in which these existence islands take place are rather limited. So they are of order unity as compared to the capillary length, but enough, they move from 2 point something to 3 point something, 3 to 4, something like that. So the existence of solutions with two films, well, they exist. That's the good news. The bad news is that you need to be very careful when you try to implement them in the lab, because of course you have a very limited range of solutions. If I have time, I would like to explain later why these solutions are so limited in the parameter space. The other interesting conclusion that we obtain is the effect of the viscosity ratio. If you notice, the viscosity ratio is represented in logarithmic scale, because we can change it by 3 orders of magnitude. So you see, whereas it has a dramatic effect on the outer film, actually a non-monotonic effect on the outer film that can even lead to the very inexistence of the film, for the inner film, you will see that it barely affects its thickness. And in fact, the isocontours in both maps, you see that they are pretty much horizontal, even though we are changing the order of magnitude of the viscosity ratio by a factor of 3, or 3 orders of magnitude, right? And lastly, the other thing that I would like to mention is that if you notice, whereas the thickness of the outer layer exhibits a non-monotonic behavior with respect to these two parameters, M and delta H, this is not the case for the thickness of the inner layer. You see that it grows monotonically as you increase the thickness of delta, you increase delta H, the thickness of the supernatal layer, okay? In our paper, we have an explanation for many of the things that I just described. Today, I don't really have time to go through them, unfortunately. Well, or fortunately, because then you may want to go and take a look at the paper. So basically, we are going to explain some of these features. And to do that, we need, of course, to take a look at the flow structure. Of course, when you solve numerically the problem, you not only have access to the thicknesses as a function of z, but you, by post-processing, you also can calculate streamlines, velocity fields, pressure gradients, shear stresses, and so on. So the first thing that I'm going to take a look at structure field, the streamlines. We focus first on the inner fluid, the fluid that is represented in blue. This inner fluid, basically, it behaves as if it was a one liquid Landau Levich problem. So you have that very close to the plate, the streamlines are nearly parallel to each other and they are moving vertically upwards. It means that there is a layer of fluid that is the one that eventually will go into the flat film that is moving with the plate pretty much all the way, since deep down into the bath to the film. Then you have this recirculating region sufficiently far away from the plate, or conversely close to the separating surface. And there, the fluid that is moving in this recirculating region is taken from deep into the bath to a region close to the interface. And then it's pulled away from the meniscus, okay? This is quite classic, and in fact, this is what happens in the one liquid flow. Now, the fun part, what happens with the outer fluid? Well, with the outer fluid, you see that the flow pattern is dramatically different. And actually, it's even a miracle that we can have two films, because if you take a look at this, whereas the inner fluid, it has the plate that is pulling the liquid up all the time, the poor guy, the poor outer film, is actually the other way around. So the interface between liquid 1 and 2 is pulling down all the way the liquid 2. Still, by continuity, if you're pulling the liquid down, some liquid comes from the free surface, from far away from the meniscus, from the bath. So it comes close to the free surface and is moved close to this region where the two interfaces come in touch with each other or come very close to each other. It is only here, as I'm going to show later, that the fluid tube, that the liquid tube, has some chance of being eventually dragged into the film. But things are not easy for this liquid because it's like, first of all, with a not very strong force, and if anything is dragged down by the interface, right? So it's kind of surprising that there is an entrainment at all. And definitely this flow pattern, we believe that it explains why we expect or we observe to have very thin films of the outer thicknesses of the outer films as compared to the inner one. So basically the flow pattern is very different, as you see, but it's also illustrative to take a look at what two other main magnitudes do in this flow, namely the pressure gradient and the shear stresses. So pressure gradients here we represent in orange the pressure gradient in the liquid tube, in the film, and in blue is the pressure gradient inside liquid one. So what you observe is that the pressure gradient is pretty much zero, the orange line is pretty much zero all the time until you get to this region where suddenly it peaks, right? But remember, this is the pressure gradient. So it means that the capillary stresses or pressure gradient coming from capillary stresses, as you see on these expressions. So this pressure gradient coming from capillary stresses, as we discussed in the beginning, what they do is try to take the liquid down. So actually, life is not easy for liquid tube because it takes it a long while to be able to reach this region where it has the only chance to be entrained. And then when it gets there, one of the things it finds is this capillary gradient that peaks precisely at this location and that still tries to take the liquid down. Fortunately, the shear stress at the interface between liquid 1 and 2 at the blue interface still peaks enough to be able to compensate for that negative pressure gradient. And in fact, the very reason why we have entrainment at all of the outer liquid is because we have, the blue line is the stress at this interface, is because we have some stresses that are, well, negative in this plot means that pull up, in this case, that pull up the liquid into the film. Of course, these stresses are tiny, are very small compared to the stresses that are taking care of moving liquid 1 into the film that are represented here by the black interface, okay? The red line that we represent here corresponds to the one liquid Landau Levich equation adapted to basically the curvature of the meniscus of interface 1, okay? Well, so you see that actually the stresses, even for liquid 1, are not very large, except perhaps in a region of a few units in terms of the relevant variables, where the stresses are sufficiently high to be able to pull the film. The fact that we have stresses that are small when you get away from this region is the explanation that we found for the fact that delta H can change so little in the existence island, because at the end of the day, if you have the interface or the two contact lines very close to each other, then basically what you are doing is to move away from these sweet spots where the stresses are maximum. So if you have the contact line very high up, then the stresses are not enough to pull. And if you go very low down, not only the stresses are not enough to pull, but actually like you would get one contact line falling behind the other or falling below the other, which of course is not a physical condition. In fact, if you go to these curves or to these existence islands, if you see the delta H that corresponds to the lower limit of existence of the two-film solution, it very nicely corresponds to the condition where the two contact lines get in touch. So basically coming here, no, not here, there, yeah. This corresponds to basically these 2 points, the 2 points getting together, and therefore, well, the delta H is equal to 0, right? Or to 0, to the limiting value you have. Sorry, I'm running a little bit because I see the time is...
Yeah, we have 2 minutes about, yeah, and...
Okay, perfect. Then let me finish with the interesting part. Okay, so I'm going to skip this slide if I only have 2 minutes. Now, take-home messages that I think I can still tell.
Yeah.
So what we have then is that we have seen that basically the stresses are pretty much equal to 0 everywhere, except in this very thin region that we call the virtual contact point, because even though the two surfaces don't really touch, actually they get super close to each other. So therefore, it means that, that we can regard this point as if it was, one point where the interfaces touch. Now, we saw that there is where the stresses are different from zero, and therefore where we can expect to have some entrainment. No? Well, what we are going to do is to relate the observed thicknesses of the films to the stresses that we find precisely at this point. We can do that very simply just by using the same scaling arguments that we were using for the one liquid problem. So basically, we say that the stress that drives the liquid one, it has to be estimated as we did in the one liquid case, like viscosity times velocity divided by the thickness in that region. So therefore, if we use the proper non-dimensionalization on this expression, we get that we expect the thickness of the inner fluid, or the inner film, sorry, to scale as the inverse of the stresses. And in fact, if we plot such a power law here, and we plot all the thicknesses that we obtain in our simulations as a function of the stress at the virtual contact point, at this peak point, you see that they very nicely follow the trend predicted by this scaling. Same thing, or a similar thing, can be done, of course, for liquid 2. So in liquid 2, things are a little bit more complicated because you don't really know a priori what is going to be the velocity at the interface, because that's unknown, that's part of the solution. So therefore, what you do is basically to say that the shear force on this region has to compensate the capillary stresses. And these capillary stresses, of course, themselves, they have to be consistent with the curvature imposed by the outer static meniscus. When you mix the two conditions together, you can do, well, you can basically find out the scale of the thickness delta H, as we did for the one liquid problem. And then you obtain that you expect the thickness of this outer film to scale as the square of the stresses at the virtual contact point. Of course, there is more dispersion because numerically this is harder to compute. But when you plot this on log-log coordinates, you see that it very nicely follows this delta H proportional to tau square. So in fact, we think that we have captured the main ingredients that allow us to explain the observed dynamics of the two films. In particular, and with this, I think I can just jump to the take-home messages. First of all, well, basically with these scalings, we are able to explain most of the things, and one of the most important conclusions is perhaps that if you want to understand what the thicknesses do, you don't really need to look at the whole flow. You need to focus on this specific point, which is the virtual contact point, where the two interfaces come together. If the stresses there are sufficiently high, good news, it is possible to get a compound coating only with one single dip. And basically, the problem resembles very much the one of the one liquid flow, although it's, of course, numerically, it's more complicated. And in particular, there is no solution for all the values of the parameter. There is only a limited range in the parameter space, and we believe we can understand why, where you actually can have the two liquids. Sorry for taking so long. I think I ate up a few more minutes than needed. Good news, we just published this manuscript on arXiv. So if you have more technical questions, of course, you can write me or any of the co-authors, but also you can take a look at the manuscript that is on the link. Okay. Thank you very much for your attention.
Thank you very much, Javier. Thank you very much. Potentially we have almost unlimited time for questions, but I understand that some participants could have another commitments and could leave. So then, yeah. But potentially we can stay. All of you can stay, and we can continue with questions. So I have questions, but I suggest that other participants ask questions first. Any questions, please? Mark, yes, Mark, please. Mark Bly.
Javier, is there anything special about the wall being vertical? Could it be inclined at an angle?
Great question, Mark. Well, actually, well, it has several effects beyond the obvious effect that is to reduce the intensity of gravity. It also introduces some transversal pressure gradient, which may have some effects. We haven't studied that for the two liquid configuration, but it's beautifully studied for the one liquid case in a paper by Wilson in 1982. And actually it was a very inspirational paper, because by studying this paper, we understood finally how to implement the boundary conditions on the two liquid problem. So it's a very interesting work. I think actually, if you let me go back to one of the previous slides, I think we had the reference somewhere here, or it should be, yeah, here it is. Can you see it, Mark? It's Wilson,
yeah. Okay.
Journal of Engineering Mathematics. Yeah, so this guy, besides doing the rigorous asymptotic analysis of the problem using modern asymptotic techniques, what modern in the 80s, no? One of the things the guy did was to incline the plate, and he basically found that the inclination has a correction effect on the thickness that he can predict asymptotically, but it doesn't change substantially the nature of the problem. So it modulates the effect of the thickness, but in the one liquid case, it doesn't really change things dramatically. It is a very interesting application, though, because when you can think of a plate that is inclined, but also you can think that this is not a plate. You can think that this is a roll that is rolling close to a free surface, and then this could be a very nice model of the coating of a roll into a bath. So this is the motivation that Wilson had when he did that. And so basically you can add an angle. It's not too complicated. This is what we learned from Wilson in the case of one liquid. In the case of two liquids, we didn't try, but if we would extrapolate the conclusions, I would say that this changes or stretches a little bit the parameter ranges, but it doesn't really change the nature of the flow. So we don't expect to see like fundamentally different things.
Okay, thank you. Could I just ask another question quickly?
Yes, please. Yes, please.
For the vertical case that you have studied, I was just wondering about for the coating problem, the region far up in Z where it's become uniform thickness. Mm-hmm. Is that stable? I just seem to remember that if you have a film flowing down a vertical wall, the critical Reynolds number is 0 if the wall is exactly vertical, mm-hmm. which would suggest that it's not stable.
I didn't think of that, but there are experiments where you see that this film stays stable for as long as you want. Well, there are several studies, but in particular, when you have this falling film, in the case of when you go far sufficiently high up and you get the gravity effects back in place, there is this paper by Javier where they are able to experimentally observe this field for, as long as they can measure. So I think, I see your point. So there you would have this inflection point in the velocity profile, and this should make things unstable, but for some reason here it's stable. I wonder if it's because within the lubrication approximation, the flow has to be 1D, and there is not much room for instabilities to grow. I wonder. I don't think the problem has been studied, actually.
Which was the experimental paper you mentioned?
It's Javier from the University of Twente. It's a physical review letters in 2008. So I can try to check the reference.
Is it in the paper?
It's Nature PRL 2008.
Reference to the paper.
Coating. Here it is. So what I can do, I'm becoming a modern guy. Let me copy the link in the chat. I think we can do this with this.
Okay. Yeah, good.
You can see. Yeah. Lovely. Yeah.
Okay.
Yeah. Okay.
Ah, Benoit, I didn't know that Benoit was here. Nice to see you online.
Yeah.
So here is the...
Javier, what we can do to make the second film more visible, thinner? So it's not, I understand it's not about gravity, but anything else, any other effects could be, very special conditions could be created to make the films at least of comparable thickness. Is it possible?
Based on the theory, perhaps your best shot should be to reduce even further the surface tension ratio, because by going down the surface tension ratio, we observe that you make the thickness grow quite a lot, up to an order of magnitude or something like this. However, it's a limit in how low you can make the surface tension ratio, of course, or interfacial tension ratio. You can always think in a first place to add surfactants, but of course, adding surfactants, besides lowering the surface tension on the interfaces, have another effects like dilatational. I mean, like surface rheology. I'm not going to talk about that, not to embarrass myself because I don't know anything about it, but I know enough to know that it's complicated. So this is something that I would think, but how much more complicated the flow with surfactants would be, I don't know. So I would be cautious. But yeah, in principle, the best shot, practically speaking, what I would do is to add surfactants.
Okay. Semyonov, Yuri, do you have question? You have question, yes. Please ask your question.
How results may change if properties of the liquids approach one to another? Density.
Could you repeat, please, Yuri?
If the liquid 1 and liquid 2 are almost the same fluids.
Yeah.
Oh, yeah. So, well, that would make things, yeah, there is a problem if it was almost the same fluid, which is that the density ratio would be very close to each other. So, if the density ratio is close to 1, the problem that we would have is here. So, I mean, like notice that this guy, 1 minus R, that would be small. But crucially, if you come to this term, right, you'll see that then delta H would have to be super large. I mean, yeah, this would make things complicated. Yeah, because basically you would have like the liquid one climbing up a lot. Hi, can you hear me? Yeah. So liquid one climb up a lot. So actually, yeah, one of the main thing is that I mean, yeah, I don't know if there would be a solution, practical solution, because at the end you would have a meniscus that would basically cover the whole.
Okay, thank you.
Thank you. Yeah, could you switch off your microphone, please? Because it's making some disturbance. Yeah, thank you very much. It's a very good question, by the way, because if the liquids are the same, so it should be the one-layer solution, right?
Okay. Ooh, yeah, but
but from this one, it doesn't come that.
No, it's very subtle. That's very subtle, and actually, that's something we thought a lot about it.
Yes.
Yeah, what happens if you have the same density, same viscosity? Well, having interfacial tension changes things. So, as long as the liquid is not exactly the same, I mean, as long as there is an interfacial tension between the two liquids and they are immiscible, then having, let me go to the flow structure. Then take a look at this interface.
Yeah.
Surface tension here. So even if the density ratio would be equal to 1, then we have the problem that I just mentioned of the meniscus climbing up to infinity, no? But even if the surface tension, viscosity ratio was equal to 1 and density ratio equal to 1, as long as you have an interfacial tension, this guy here, this interface, is going to impose a pressure jump between the two liquids, and that's going to completely modify the flow field. So nice. I mean, as long as the liquids are immiscible, the problem is not really easy to assimilate to the one liquid case. Now, if you talk about miscible liquids, that's a completely different thing, and then you're right. If the liquids are miscible, then yes. Then if the properties are the same, it's better liquid.
If you set coefficient of surface tension on the interface between two fluids 0, does it help?
Then you have the case of miscible liquids that we haven't considered. That could be interesting. Yeah, I guess that in that case, you could probably have always two films.
Okay.
Yeah. Well, I mean, there is something interesting, which is that if you set to 0 the surface tension of the interface between the two liquids, well, first of all, we need to change our notation because we use that surface tension to make the problem dimensionless. So the formulation that I have described would need to be changed because otherwise it's singular, right? Okay, but that's a minor problem because, of course, you can always use the outer in surface tension, so that's easy to avoid. No, but the thing is that based on what we see, the smaller the surface tension ratio between the two liquids, the thicker the two films would be. And why this is the case? Because I said before that capillary stresses try to oppose the formation of the films.
Yes.
So of course, if you avoid one of the two interfaces, then the films are going up.
Yeah. So I believe when you was talking about surfactants, so you are thinking about changing the surface tension.
Exactly. Yeah.
And or particularly if you increase the temperature, then it's another way of reducing the surface tension, for example, right?
For instance,
so then you can control the thicknesses. Okay.
No, the question by Yuri was excellent because actually it's something that we thought about carefully, like, you know, in which limit of the asymptotic or the parameter range our films behave as one. I mean, as long as there is interfacial tension between the two liquids, it's always a different flow. It's in many ways to explain, but it's totally a different flow.
But also, Javier, I remember there is a reference in the paper about somebody modeled the textile as another very viscous fluid. So in this case, if the fluid, which is close to the wall, is kind of very viscous, so then the wall together with that fluid, it can be considered as another wall in some sense.
Yeah, exactly.
Right? So that is kind of inversion of the Yuri question.
Yeah, well, but still, the thing is that interface 2 still it has a surface tension. So even though you could say that the viscosity of the liquid 2 is small, then viscous effects would not greatly affect the inner film. But still, curvature is there, and the surface tension is going to be acting there. No? Actually, this is something that is consistent with what we see. So you remember that in this plot, in these maps, we discussed that we see that the viscosity ratio almost doesn't affect the inner film. You see that these isocontour lines, they are nearly horizontal, right? So we already see that the viscosity ratio has very little effect on the thickness of the inner film. What really changes things is having another interface. So surface tension is a big thing in this flow.
And if we return to your very first slide, there were two parts. On the left, it's the title of your presentation, and on the right, you said something from future, future experiments. So, do you think that this is feasible to make experiments and to measure thicknesses and to arrive at, say, technologies covering something with two fluids at the same time?
Well, actually, we are optimistic about that. Thank you, Sasha, for asking, because this is one of the slides that I had to skip for lack of time. So now I have the chance to show it. So we are already working on that, and this is actually one of the main goals of the Marie Curie project of my colleague Leganes. So we are starting to conduct experiments. The good news is that so far, working with one fluid, we are able to visualize using laser fluorescence. Laser-induced fluorescence, we're able to visualize the film. So you take a look at the left panel. This is the dynamic meniscus region. So this is basically we have like a liquid bath with a plate, like the one we saw on this figure, and then we shine a laser sheet at the meniscus, like you can see here, marked sort of in red. No? So then when you look with a microscopic lens at this region here, you see things like the ones we have on the left. This is done for the case of only one liquid. And then we see this nice curve here. This is the static meniscus, or the end of the static meniscus. And you see that it matches with this region where you may see this very thin line. I don't know if you guys can see that on your screens. This very thin line is the image that we get from the film. Is the fluorescency coming from the film. So we are doing this for the one liquid case. We have checked that the thicknesses that we measure with this technique, they scale as the capillary number to 2/3. This is good. Still, we have some issues with the calibration, but we are working on that. But definitely we recover the Landau Levich scaling. And these other figures that I have here on the right, they correspond to very first experiments with two liquids. So basically here we were checking that we have the liquids glowing in two different colors, so we can use filtering to tell the two menisci apart. And we are working there to be able to see the two films, or at least one of the films, no? If the other cannot be made fluorescent. So this is what we are working on at the moment, and yeah, we're very optimistic. We think that the experiments are going reasonably well.
Yeah, thank you.
Yeah.
Benoit, do you have something to add to the presentation? Benoit, because Benoit is with us.
I saw it when I entered in the chat to post the link to the PRL paper. I saw Benoit. So
Yeah. Nice. I just arrived a little bit after the beginning, but I could follow most of the talk. Great talk. Nice presentation.
Hey,
very good. Very good.
Yeah, I can add something that we also mentioned in the paper, that this can be somehow easily applied also to fibers, coating fibers, and double layer coating in fibers might also be an interesting application. Yeah. But I think is that exactly like for one layer liquid, this whole theory can be extended. And also, as you mentioned earlier, for inclined, I mean inclined plate, because many coating processes involve inclined objects actually in real life, like in galvanization, or so. I mean, this really it's a good background for all those extensions.
Yeah, indeed. Yeah. Benoit is very right. It's a nice presentation, Javier. Very good. Very good presentation. So it's can be a lecture for somebody, but hi, Benoit. Hello. Yeah. So, but we are recording this lecture or lecture presentation, so it could be available to others. So actually we're recording just for Davide, but we can put it, if you're okay, on YouTube, say, and then the people could enjoy. Yeah,
perfect. Yeah, that would be lovely. Yeah, and
okay, and also the kind of to advertising your paper. Yeah, very good. Yeah.
Our paper.
Our paper, and many thanks and congratulations should go to Lion.
Yeah.
Okay, yeah.
So this is you want more for the next day, okay?
Yeah.
This is just the preview.
Yeah, I think, this hot topic, another hot topic.
Yeah. Cold things are hot topics.
Yeah, always hot topics. Any other questions, Mark Bly? You are still with raised hand? No?
Oh, sorry. It doesn't tell you that you've got your hand up, this thing. Okay.
Okay. So, no. I think.
Yeah, it's really nice talk, Javier. I really enjoyed it.
Smart.
Very good. Thank you very much. Thank you
for attending, and thanks for the invitation as well. It was a pleasure to give this talk. I was really happy to see you guys, even if it's only online. And I wish that soon enough we can also meet in person and do experiments involved with more interesting fluids.
Yeah. Okay.
Thank you very much.
Nice to listen to you. It's nice to hear you.
Yeah, very good.
Hi, Tanya.
Hi. Yeah. It's pity that Lion has no camera, so then all of us would be on the Yeah, okay, then we close our seminar. Thank you very much to all participants and speaker. It was great and very good questions, and there could be some ideas for future research and inspiration to others. Thank you very much.
Thank you, guys.
Bye
Take
bye.
care. See you around.
Yeah,
Bye-bye.
yeah.
Bye.
I stop recording. Stop recording first.